All right. I think we can start now. Good morning, everyone, and welcome to Texas A&M University Society of Petroleum Engineers Technical Training with SEMTech. It's a great pleasure to have three experts joining us from SEMTech today in order to discuss hydraulic fracturing modeling on ZFRAC-RE and EDFM. Before we start, this training is going to be recorded and it will be distributed among the attendees after we finish today. And also, if you have any questions, please send them to the chat box so we can address them to the speakers today. And before we start, let me introduce our guest speakers, starting with Dr. Wei Yu. Dr. Wei Yu is the Chief Technology Officer at SEMTech. He is an associate editor of the SPE Journal and the Journal of Petroleum Science and Engineering. His research interests include embedded discrete fracture model EDFM, technology for modeling complex fractures, and EDFM-AI for automatic history matching. Dr. Wu has published more than 150 technical papers and 3 books. He holds a PhD degree in petroleum engineering from the University of Texas at Austin. Thank you, Dr. Wu, for joining us. Next is Joseph Lins. He's a petroleum and software engineer at SEMTech. Joseph is responsible for writing, testing, and maintaining algorithm codes for SEMTech core applications in both conventional and unconventional resources. He holds a BS degree in petroleum engineering from the University Central de Ecuador and a master's degree in petroleum engineering from UT Austin. Thank you, Joseph, for joining us. And last but not least, we have Chu-Shu Liu, is an engineering intern at SEMTech. He has been responsible for developing and designing EDFM-AI, URSIM engine and interface, and EDFM and ZFRAC-RE interfaces. He has extensive fracture reservoir modeling experience with EDFM. He holds a BS degree in petroleum engineering from Penn State University, a master's degree in petroleum engineering from UT Austin, and he's also a PhD candidate at the University of Texas at Austin. Thank you, Lou, for joining us. And now, without any further ado, we'll leave the floor for you guys, and I will allow the sharing as well.
Okay, thank you, introduction, Kazem. Yeah. So we can start now?
Yes.
Okay, morning, everyone. Thank you, SPE of Texas A&M University, to invite us to give today the seminar and the software training. So based on our time agenda, first, we have 3 talks talking about our software and some applications. And after 3 talks, if you have any question, we can discuss the question. And after that, we will have one session for ZFRAC fracture modeling software training. And we will, and Dr. Liu will give a demo how to step-by-step use the software. So everyone, if you are interested in the software to do your research or homework, something else, let us know, and we will share the release the license for everyone to use. Okay, maybe let me share my screen. The first talk is by me, so I will talk about. Let's see. Can you see the screen, right?
Yes, we can.
Yeah. So the first talk is from me. I will talk about our ZFRAC-RE software for hydraulic fracture modeling and calibration. And after my talk, and Joseph will talk more about the details of ZFRAC simulator. And after Joseph and Dr. Liu will talk about AI to couple with the fracture model and the reservoir model to do automatic calibration. So this is my talk's overview. First, let's talk about the hydraulic fracture network, and then show our ZFRAC-RE software, and then discuss some applications using EDFM technology.
Dr. Wei.
Yeah.
We are seeing a couple of boxes, or black boxes on the screen. I was wondering if there's a chance to remove them. Maybe there's, like from the Zoom application, Yes, that one and one on the at the bottom.
Okay.
Cannot let us see. Okay.
Oh yeah, this one.
Yes.
This one. Let's move. How about now?
Now is good.
Okay, thank you, Joseph.
Okay.
For unconventional development, I think in US we have more than 10 years, and we try to understand hydraulic fracture and to optimize the well development. So based on this progress of more than 10 years, we know hydraulic fracture, we should have like 2 different types. One we can call wetted hydraulic fracture, or like unpurposed hydraulic fracture. Because when we do hydraulic fracturing, we know we will pumping a lot of water and sand. But you know the water can transport much further than the percent of sand. So the total hydraulic fracture we can call wetted fracture. But when you go to after completion, we go to production, so the hydraulic fracture will be closed. And ideal, we want like this. We want a percent and water can go further and further and together. We don't like this. But in reality, maybe we know the water can move much faster than the sand. So that's the reason when you go back production, and this part will be closed. So that means we waste a lot of money to pumping more liquid, but not useful for the production. So that's when you do completion optimization. So we try to maybe avoid pumping too much water, because water also need money. So that you can imagine, if we can have a better percent, because percent like sand is easy to settle down. If we have like a very light percent and can move with water easily, then I think our unconventional production will be easy double. So that's, I think, most people, they work on percent optimization. They try to have new material, maybe to replace the current percent. That will be another breakthrough technology for unconventional. So when you optimize the well spacing, so the key thing we need to use effective fracture, like or you can call purposed hydraulic fracture. So that means I said here we have another type called effective fracture. So effective fracture length and height is very important to determine the well spacing. Because for unconventional development, we often use a pad. One pad includes multiple wells. So well spacing is more important. So it's better using effective length and effective height, not use the total wetted fracture length and height. So that when you do completion optimization, so that's the first goal we need to achieve. The second one we try to achieve called fracture uniformity index. So the equation is very simple. It's equal to 1 minus standard deviation divided by mean. So if all the hydraulic fracture, they have equal length, equal height, and you can see the standard deviation will be like 0. So the UA is equal to 1. So this is our goal, to optimize the fracture. If you have the very good UI, then you will see a very uniform drainage, and you will have very good production. But in reality, we know hydraulic fracture will compete each other, and it's difficult to achieve this uniform fracture growth. Most time like this. So some fracture will grow much longer, and some hydraulic fracture will grow very small. So the UA is almost smaller than 1, and most case many years ago, the UI maybe like 0.6 is not very good. For that reason, in US, we have another new completion. Maybe you know, we call limited entry or extreme limited entry. How to achieve that? So we try to limit the number of perforation because before that we have maybe more than 10 perforation per fracture, and now we can reduce to 4 or 2. So the perforation number is small, and then you will have a very significant perforation friction pressure, and then you will have better UI. Or you can reduce the perforation hole diameter. Similar, you can achieve higher perforation pressure. So that's the reason in recent years, during our completion in the field, we often use limited entry or extremely limited entry. You can achieve much better. You see the 0.9, very high uniformity index. So that's very good. So when you do a good fraction job, so we should have a much longer, much higher hydraulic fracture, effective fracture length at height, and also much larger UA. So that's our two goal when you have a very good completion. So because underground, we try to understand what's the effective fracture length and height, because it's difficult to see directly. So in recent years, we have a lot of fracture diagnostic technologies. Based on my understanding, two technology we often use. One is fiber, especially we have a production fiber. When you put a well, go back to production, we have a fiber to identify the effective length and height. Second, we often use is downhole gauge. That's much cheaper than the fiber, but it's very useful. You can put a lot of pressure gauge along the horizontal well. So you can imagine if the production well go to production. So if you have a pressure here from the neighbor well, so you will see the pressure draw down. That means the hydraulic fracture grew to here. So that's very useful tool technology today by fiber and downhole gauge together to calibrate the effective fracture length and height. So that blue color called total fracture length and height. You can call unperped. This is called perped. So with these two technology, and people are very smart. They design something like called slanted well. You can see here we have two well designed by ExxonMobil, and you can see this monitor well, slanted well, they are not parallel to the P1. They have some angle, and you will see the monitor tool is not in the same layer, is in across different layer. So that's easy to identify the height. So this design is a very modern design and very smart. So based on these two technology and the slanted well, now today we have a better understanding of the hydraulic fracture, but that also give us a lot of challenge how to calibrate your model. So that's the reason in our hydraulic fracture model, we must honor this diagnostics. So after calibration with this monitor data, and then you can see we can optimize our fluid pumping. Like you can reduce 20% or you can reduce 40%, but still you have a similar effective fracture length and height. Then you can save a lot of money. You do not need pumping too much water. So another key learning from US DOE sponsored HFTS hydraulic fracture test site. And we have a lot of learning. for the fracture complexity, and especially we know we drainage many well. They are very close, as they always have well interference. You can call fracture driven, or maybe fracture hit, especially for some field. If we have a natural fracture, the natural fracture will increase more fracture complexity and more well interference. So that's the reason why we need to develop a software not only handle single well, we must handle multiple well together, because they interference each other. So you cannot treat them one by one independently. And because unconventional, every day you drill the well, maybe every day you can pump in maybe 5 stage average. That's the reason our modeling work need also to follow the data, to analyze the data. But however, we know today, when you do physical simulation like fracture modeling and reservoir simulation, the efficiency is very important. But today, we still, in the fracture simulator, we have a lot of commercial one, and we found the efficiency is still a big problem. So we cannot analyze the data very quickly. So that's the reason, if your simulation time is take a long time, how to do that? So we need to do simplification. Maybe we only can try to model single stage, or maybe 2 well, and maybe each well single one stage. So we cannot model quickly multiple well and multiple stage, because we have no better choice. That's efficiency is very important. So that reason, when we develop our software, we try to overcome this limitation. And second, in some field, we have a lot of natural fracture. And most time they are 3D natural fracture, not a 2D. Maybe they have some deep angle. But currently, there is no software to handle this 3D fracture. They only consider like 2D. They don't care about deep angle. Always assume natural fracture 90 degree of angle. So that's if you cannot handle that, but you can still do some simplification. And reservoir simulation, similar, we use a very traditional unstructured grid. And you will see that if you use unstructured grid, simulation time is also a big problem. And also today we know the AI, many people work on AI area. So we need to use the powerful AI tool to couple the fracture model or reservoir model to run many cases to calibrate your data. So that reason, based on the current from geology and geomechanics and the reservoir simulation, the whole workflow, there are some limitations we try to solve. So that reason, from SimTech, we have about 7 years of history. So we develop ZFRAC hydraulic fracture simulator and RE reservoir simulator together to overcome the limitations. So that's the picture you can see. We can honor 3D natural fracture. You do not need to do simplification to vertical 2D fracture. So you just honor the geologist natural fracture characterization work. Secondly, we have because the shell, they have some horizontal fracture, or you can call bedding layer. So you should honor this, because the horizontal fracture will affect hydraulic fracture height growth, and also maybe some fault. So this we show one example, single well, and you see 3D natural fracture and some bedding layer and some big fault to model the hydraulic fracture growth. especially this year, I attend the NVIDIA the conference. So a lot of AI fans attended the meeting, and we have very powerful GPU. So I think in oil and gas industry, we also need to update our software, either fracture simulator or reservoir simulator, change from a CPU mode to a GPU mode, because the GPU you will have more than 10,000 core, so that will speed up your simulation significantly. So today, I think Liu will show our GPU reservoir simulator. You will see the speed up is significantly. So, and also the AI, because we have a lot of AI tool, so we can couple the existing AI method with our physical model together to do simulation. So that's like we use XGBoost. We tested a lot of AI method, and we graduated many master students in university, just because no AI is no one is the best one. So different AI, they have different advantage. So currently we tested a lot. We found XGBoost is currently best one to couple our hydraulic fracture simulator. And then based on the AI, and you can calibrate the pumping pressure automatically. And you do not need to run too many cases, and you can get a very good match for the surface pumping pressure. And then you can get the hydraulic fracture geometry. And we already tested this very well. So if you maybe in the software demo, you will see that how AI work with ZFRAC. And another application is AI coupled with our EDFM, the reservoir simulator. The EDFM is an embedded discrete fracture model. We work on this technology more than, I think, 10 years. We have several US patents. And that reason with some AI, you can do smart sampling, and you can have very good learning to tune your hydraulic fracture effective length and height. A lot of uncertainty. You do not need to manually change. Just based on the AI method can change automatically. So that's a very useful and efficient to do calibration with your production data. So with our more than 10 years development history like EDFM, because more than, I think, 60 years ago, like 1960, we tried to simulate a 3D natural fracture production like this. You see, this is not a vertical fracture, it has some deep angle. So 60 years ago, we have a dual porosity model. It already, this method already go to our textbook. So maybe you are a reservoir engineer, you need to learn dual porosity model. You can see, because we cannot model 3D fracture like this, but we are smart. We can assume hydraulic natural fracture is everywhere. We can do like this. This is a very smart assumption. Even today, we still use this method, but you cannot see the fracture like this. So the accuracy is a big problem, but the efficiency is good. But for 3D, no, we cannot do that, but we only do this like 2D. And then like in 1980 around, we have a commercial reservoir simulator. They use a local grid refinement method called LGR method. You can exactly see the fracture. Here you see two fracture, but these two fracture is simple, only orthogonal. You cannot have a different shape, always like this. So the accuracy much better. We change a lot, but you will see we will have a lot of grid refined nearby this fracture, so the efficiency become big problem. But still 3D, like with deep angle, this method no way to do that. And then this like Schlumberger company with Total and Chevron together, 3 companies together, they try to overcome this limitation. I think they invest more than 10 years, spend a lot of money to commercialize called unstructured grid. So unstructured grid, you can see it's more beautiful to capture this complex fracture network. But still for 3D is no way, because unstructured grid is difficult to generate this smaller grid if you model 3D fracture. But also you will generate a lot of small grid, so efficiency still a big problem. For that reason, 10 years ago, so we work on EDFM method. So this is we commercialize this technology. Is very powerful. We can easily model 3D fracture. This method, after 10 years development, I think it become a standard to model this either 3D natural fracture or very complex hydraulic fracture network. And the key advantage and innovation, you will see that the EDFM method, you do not need like a smaller grid nearby fracture. That's the key breakthrough. So hopefully you can learn this is the best method to model fracture for production is EDFM. So the EDFM, this is a little bit more detailed workflow. So if you have 3 matrix grid, and then you have like 3D fracture. Like fracture 1 is very long with some deep angle, and the fracture 2. So you can imagine if you use the local refinement, because no way either with the structured grid or unstructured grid, we cannot local refinement these 2 fracture. But with the EDFM, and we can see we use it in the simulation area, and we have some fracture grid. Like fracture 1, we have 3 grid, and fracture 2 we have 1 grid, and we do not need to modify the matrix grid, but they talk to each other. And in reservoir simulation area, we have a keyword called non-neighbor connection, and we just change the non-neighbor connection and transmissibility. This is Darcy's law. So we just modify Darcy's law transmissibility, and you can easily to model production. So now you will see the key difference between unstructured grid and EDFM is we do not need a local refinement. So like this is realistic geo model and put a lot of big natural fracture. I will see we have 2 grid. One is the geo model matrix, and then another is the fracture grid. They use the non-neighbor connection and transmissibility coupled together. So that's very powerful. And we did a lot of benchmark, because new method you need a benchmark with some existing method. So the accuracy is okay, and the efficiency is much faster. The key reason you will see that we do not need too many grid of matrix grid to handle the fracture. And especially for when you do naturally fracture radar for water flooding, one water injection and the producer. So you will see the fracture, they are not connected. So if you use the old dual porosity method, because the dual porosity method will overestimate their connection. The method will assume they are connected to each other. So it's easy to have a water breakthrough, because they connect each other by DPDK method. But EDFM can accurately capture this non-connection of a fracture. So that's the transmissibility is quite easy to understand, because this is Darcy's law. The transmissibility only depends on these 2 grid, like distance and area and permeability. So that's it. And that's the reason we write the EDFM book. So if you know Darcy's law, and easy to, based on the book, you can calculate this distance, area, and permeability, including like these 3 type of connection. Like you have a matrix for fracture, and in the single fracture plane, you have a lot of small fracture segment. In one block, you have maybe 2 or more fracture interaction. The last one is a fracture well intersection. So that's the key of EDFM theory. And then with EDFM, we can using a polygon to model fracture boundary, maybe like hydraulic fracture, not like always rectangular or circle. For example, maybe like Texas shape. So we can use some polygon to model this boundary, and you can easily to simulate the production from Texas shape fracture geometry. And EDFM is very friendly. You can do plug-in. You can transfer or couple any hydraulic fracture geometry from this commercial fracture simulator like us or Celebrity Kinetics, Halliburton, Gopher, Implan, MFRAC, or FRAC-Mac, Petrol. And we can transfer to all these reservoir simulator of commercial like Echelon, URC, Eclipse, CMG, T-Navigator, and others. So for fracture modeling, the key input is like 3 key input. The first is stress. The stress including minimal stress and maximal stress. So that's the first key input. Second is Young's modulus. Last one is the Poisson ratio. So when you do hydraulic fracture simulation, you need to have these 3 input. And this is called rock properties. And after that, then you can input like how many well and like how many perforation, and you can optimize the well spacing like from 200 to 400. You can design by yourself. And then you can input the 3D natural fracture, because the natural fracture in US shale basin mostly is very popular for like Marcellus shale, Harness Well shale, and Austin Chalk, and Eagle Ford. So, and if you have a natural fracture characterization by geologists, and then we can easily input from their work. And then you can do fracture modeling to understand the fracture interference and some natural fracture activation. So after that, then we can do some calibration, and then we can move on the production to see how distance of the well spacing is optimum to produce more production. So that's the ZFRAC-RE you can use to do a lot of research or project study. So last, I will quickly show some applications. We work with the Saudi Aramco to test EDFM capability because EDFM is very powerful, and we try to handle 1 million natural fracture. And the reservoir model is very big, and we put like 400 well, and you can see total fracture like 44,800 number. That's the biggest test of our EDFM capability. We can model like a median level of a fracture, because underground natural fracture is almost 7 million, not a small number. Second, we can do microseismic. This is a very old, more than 10 years ago. We often use the microseismic to understand the SRV, stimulated reservoir volume. And we know the microseismic will overestimate fracture size, because this is like the total fracture cannot monitor the effective fracture. So when you go to production, we must do some cutoff to reduce fracture height and length to understand the effective one. So this study, like the first shale gas well in Middle East, we worked together with ADNOC company. They drill first well shale gas, and they use a microseismic to understand the total SRV. And you can see the fracture length is much longer, like more than 1,000 feet, and the fracture height is 75 feet. And then go to production. In order to match the production data like gas flow rate, water flow rate, and bottom hole pressure, and you must shrink their fracture length and height. And you can see the fracture length will cut off more than 40%. So 40% and overestimate by the microseismic, and height overestimate 60%. And EDFM also can be used for like geomechanics. Geomechanics meaning we need to understand the stress orientation and also stress the magnitude, because when the well go to production, the pressure will decline and the stress will decrease, and also maybe the orientation of stress will be changed. If you understand this very well, then you can go to the field to do infill well or new well drilling, new well completion optimization, because you need to consider this depletion effect. Or you can do some refraction job, considering this stress change. So the EDFM can model complex fracture, then we can honor the natural fracture and the complexity very well. Without EDFM, you only can consider simple geometry. And another application called CCUS. When you do CCUS, the first you need to consider some fault. When you pumping more CO2, maybe the fault will be activated. So currently, because fault is quite complex, so without EDFM, it's difficult to handle that. But now we can easily to handle fault activation, and also you can honor this more realistic 3D fracture network to do CO2 injection. And then geothermal. So I really like DOE sponsored 2 geothermal big project. One is Utah Falls. Second one is by the first geothermal company, Fervo, also in the Utah. So it's a very hot topic. So when you do geothermal, we must honor this well interference and also 3D fracture network, because you will pumping cooled water and produce hot water. So if you use a simple fracture model, I think the simulation will be not realistic. So that will help a lot for the geothermal optimization. Last one for carbonate naturally fractured reservoir. Without EDFM, we often use a dual porosity model. In some cases it works, but in some cases it doesn't work. Especially when you do like water intrusion or water flow from bottom to the well. So if you don't honor this 3D natural fracture, it's quite difficult to understand this water moving. So that's with EDFM. We have this new workflow, and also we have the US patent to change the old workflow. And then with the EDFM, you can have a different group of the fracture network, like cross well bore. This, if you know image log, we can generate a lot of cross well bore natural fracture. That fracture is very important tool for production, as maybe some near well bore fracture and whole natural fracture. Maybe different group, they have different property. We can easily separate them in the model. We test a lot with the EDFM and dual porosity model. And you can see dual porosity model sometimes overestimate their connection. You will have a very early water breakthrough, but EDFM can capture much better. And we did some real field application. You can easily to see this some 3D natural fracture to understand water intrusion. And we honored all this geologist work as it match the water in Turin, and after maybe some year, you can see a very early water breakthrough. So that's my quickly talk. By SimTech, we develop EDFM. Is a very powerful fracture simulation method compared to dual porosity and local refinement. And we develop the ZFRAC-RE software. We use EDFM to model fracture. Then we can make our modeling work more realistic. And AI, I think Liu will talk about that. AI will help a lot to speed up the history match. Okay, thank you, everyone. That's my presentation. Yeah. If you have a question, we can discuss, or we can move on our next talk.
Thank you so much, Dr. Wu. If we don't have any questions, maybe we can move to the next presentation.
Okay, I think we can start. Let me share my screen. Okay, can you guys see my screen?
Yes, we can.
Okay. I don't think that I can get rid of this thing, but I think it's minor. Okay. All right. First of all, thank you very much, the Texas A&M SPE chapter, for inviting us. It's really a pleasure to introduce you the latest stuff that we've been doing at SimTech. Here I have the chance to present ZFRAC-RE, a powerful hydraulic fracture simulator driven by field observations. So as an outline for today's talk, we're going to discuss a small introduction, description of ZFRAC-RE, and 3 cases studies, highlighting the effect of bedding layer spacing and height growth, 3D geomodel fracture propagation simulation, and a refractoring case, and the summary. So let's check about how ZFRAC works. Basically, it's an integrated fracture and reservoir simulator in one platform. So basically here, the experience that the user has is that it can do many things in just one software. Basically integrating a hydraulic fracture modeling, a reservoir simulator, ZFRAC-AI as a calibration tool for hydraulic fracturing. And we have the representation of all those fractures using EDFM. So here in this plot, I'm showing you how general workflow is generated in ZFRAC. We start with geology and geomechanics. We can have either well logs or a 3D full rescue model representing the reservoir. All geology and geomechanics are honored here. And then ZFRAC-RE is used for reservoir modeling. We use EDFM to represent the fractures. And as I mentioned, URSIM has a reservoir simulator and an AI tool to perform fracture calibration. Then we have a really nice visualization manager here, 2D high quality dynamic visualizations, as well as 3D dynamic visualizations. So ZFRAC-RE basically is an end-to-end fracture simulator. We integrate fluid flow, hydraulic fracture propagation, rock deformation using the displacement discontinuity method, rock discontinuity interactions, which we will observe later on, physical observations directly from the field as captured in ZFRAC-RE, and we have an unconventional reservoir simulator. We possess an intuitive interface. The user, the modeler, will have the chance to facilitate his or her experience here in ZFRAC perform high quality representations of subsurface using all the tools available in ZFRAC-RE. You can include key physics in your models, include stress shadow effects, dynamic fluid rate distribution across all the clusters, and interactions with rock discontinuities, and also modeling leak off into those discontinuities as well as their matrix. One of the key advantages here is that ZFRAC-RE is powered by EDFM, which provides you exceptional speed and high resolution. So what we're trying to do here is to honor field observations at the highest detail possible, so you can better perform your optimization. So here's how we represent those 3D discontinuities. In the figure here, we have a 3D DFN showing several natural fractures distributed in a DFN model. We also can have bedding layers, which are present in most of the shale reservoirs across the US and other parts of the world as well. Also, field scale of pad scale faults can be included that may have some repercussions in your treatment. So basically here, we state how we can model hydraulic fracturing driven by field observations in one single platform. Here, let me show you a quick animation of how those hydraulic fractures can propagate in a reservoir. So this one has 3D natural fractures, bedding layers, and also some pad scale faults. So as you can see here, we are able to perform a stage simulation, fracture propagation in this reservoir, and observe the dynamic growth and intersection and subsequent effects that we can characterize in this reservoir. So that's the cluster number 2. Stage number 2, actually, yeah. And basically, the whole animation shows the implications that we can have if we actually include field observations directly on your simulations. Another thing that we can say about ZFRAC that it doesn't allow you just to model one single well. We have the ability to model several wells, multiple wells, cases, and that's the really nice thing about it, that you can do most of the things with exceptional speed. Currently, we are working on or testing actually a real-time functionality, which will provide flexibility to perform hydraulic fracture changes on the fly in the field. So this is an application that we are currently working. We're really happy with the advances that we have had. So it's going to be in the future another exceptional ability of ZFRAC, allowing you to obtain the data in real time and perform simulations on the fly. Now let's go to the actual applications. Let me show you how we use ZFRAC to model the effect of bedding layer spacing in height growth. So as you can see here, these are some pictures from different shales in the US and also in Argentina. So all of them show us field evidence of bedding planes presence directly from the field. Not only we can see them in outcrops, but only using image logs. So there's definitely some field evidence about their presence. Several operators have also told us their reliefs regarding the influence of bedding planes existence in shale reservoirs. So some of them actually believe that in some reservoirs in China, in this case, you can actually see a pressure increase or pressure spikes product of the presence of bedding layer. So basically, at every time that hydraulic fracture height is under development, if you hit a bedding plane, then there's a pressure stabilization for a time until you build up enough pressure to break that bedding plane. So those operators believe that the presence of those bedding planes or bedding layers are definitely involving several physical phenomena that can be explained through the surface pressure observed in the field. So we are able to include those effects in here, and I'm going to show you what will be the results of that. So on the left, we are showing how bedding planes are actually stimulated during a hydraulic fracture treatment. We see that they are at every time step in the simulation. They are also growing in time, and that is what we can see on the left. And on the right, we see not only the influence of bedding planes in every time step of the simulation, but we also see the influence of nearby natural fractures that are activated in every time step in the simulation. So we can actually capture the dynamic growth of bedding planes and the influence with 3D natural fractures or faults. So in this case, we're in charge of this high resolution model. Basically, we have an interval that is around 20 meters. And here we are gonna build a 1 centimeter thickness model. So basically 2,000 layers in total. So the idea here was to completely honor the operator's data at the highest possible resolution. And the input model data here is the standard model, standard input models, Young's modulus, Poisson ratio for pressure, maximum and minimum characterized horizontal stress, and fracture toughness. So the case design for this is how we can evaluate the presence of bedding planes in the fracture propagation. So the idea here is to produce 3 scenarios and analyze the influence of those bedding planes in fracture growth. Case 1, basically no bedding planes. Case 2, 20 bedding planes at 1 meter spacing. And case 3, 200 bedding planes with 0.1 meter spacing. Part of the modeling parameters controlling the bedding planes propagation and development are the mode 2 stress intensity factor, which was characterized from the field, the friction coefficient in the interfaces, and the bedding layer leak-off factor. So here I'm showing you the representations of every single case. The no bedding layer case are shown on the left. The full view of it shows you the expected height. In this case, the case on the center showing you a reduction on height with the 1 meter spacing case. Definitely a different picture in the fracture geometry. And the more radical one, 200 bedding planes, which shows you how fracture basically is unable to grow because of the presence of all these planes that limit fracture growth. So for the no bedding plane, we can see here in the animation the normal development of the fracture from the starting to the end of the simulation. For the 20 bedding planes, we can see how fracture grows, but also is activating at the same time all the bedding planes. And the same with the final one, where fracture basically is completely arrested, producing just a small fracture height and also length. So to show you the results, final results of this run, the first thing that we have to highlight here is the computational time, which is very low for this analysis, around 655 to 850 seconds of run, which is highly affordable for the modeler, which provides you with a tremendous insight on the value of the simulation. And basically here are the results. Fracture half lengths. We can see the reduction product of the significant fluid leakage leading to a fracture and reductions on fracture half length and fracture height. So here we can see a really nice application of ZFRAC-RE that allows to optimize and see better treatments or other type of optimizations in this particular stage, honoring the data at the highest level possible. Next, I'm gonna show you a 3D geomodel fracture propagation simulation. But the first thing that I wanted to highlight here is how field evidence suggests the presence of natural fractures. In this case, this is a picture taken from analysis from Gale et al. 2021 about natural fracture activation in the hydraulic fracture testing site number 2. So here's evidence of the natural fracture activation during hydraulic fracturing. The analysis of the outgrowth of the actual course also tells you presence of natural fractures. Their extent or their influence is definitely different from shale to shale, but in our understanding, in our experience in other basins around the world, the importance of natural fractures is higher. For instance, in Argentina, in the Vaca Muerta shale, or in the Sichuan Basin in China, natural fractures, bedding planes, and faults have a larger influence because of the stress state in those reservoirs. Normally in the US, the stress environment is a little bit more relaxed, but in some places, the natural fracture influence definitely is important to consider. So here I'm showing you a 3D geological model, a corner point model with more than 5 million grid blocks generated from the well-known software Petrel. This software, simulation actually not only had not many million blocks, but also every one of them contains a geomechanical property. So it's a fully 3D model generated here. The minimum grid thickness is 1 feet. And actually I have 7,000 DFN, natural fractures, in this model, obtained from one of the most important bases in China. So here in this plot, I'm showing you SH mean and how the range from 85 to 95 megapascals is distributed in the reservoir. For the model parameters, this particular model not only have that, but also SH mean, SH max, SV, Poisson ratio, Jones modulus for every single grid block. Here we highlight the fracture corridors that were obtained through seismic analysis and geological analysis as well, which determine how these fracture corridors develop in the subsurface. And as we can see, they definitely have an impact because intersect directly with the well trajectory and the subsequent hydraulic fractures propagating here. So here in this particular reservoir, fracture diagnostics suggest in other sites of this particular place small fracture height, and that's how the operator have observing in the field. So field evidence suggests you that, and the idea here is to use ZFRAC in order to honor that. Normally, when you don't include bedding planes, you obtain a large fracture height. So as you can see on the bottom left plot, we obtain fracture heights of 256 feet, which is quite large for this reservoir, and it tells you a completely different story of the actual observations. So after including bedding planes, their influence, fracture height can be contained. So as we can see on the bottom right plot, the fracture height reduced to 52.5. So that's one of the big applications of the model, that it not only lets you to include flexibility in the model, but also capture what is observed in the field. The average runtime for both the scenarios is less than 30 seconds. So as a modeler, you definitely want to experience a really good speed, but also balancing the quality of results which you are obtaining in ZFRAC. Let me show you here the hydraulic fracture development and subsequent fracture arrest in height, and also intersection with the fracture corridors that are present in this reservoir. The next case, let me show you a refracturing case. So this one, basically, the workflow starts by acquiring the stress field distribution using any other software from the industry. So when you include one of those stress field distributions, you can start modeling your hydraulic fracturing process. And what you observe on the top, the top is the original hydraulic fractures, showing you the minimum horizontal stress. So the first thing that we observe here is that the fractures range half lengths are from 90 to 110 meters, and they are straight fractures, or planar fractures in this case. The thing is that after production, the stress environment changes. There's definitely changes in the SH min, SH max, the stress, and you have to recalculate the in situ stress field again. So after you do that, you can start modeling refracturing. So here, the idea is to update the situ stress state, including all the long-term production effects. And the difference is quite large. We can see definitely variations on the stress field. And eventually, when you perform a refracturing model, you will see more complex fracture network shape. So the fractures here definitely have a different path regarding the previous ones. They try to go to places that have less stress, and their growth definitely produce different results. So here in ZFRAC, we're able to represent that and use it for refracturing processes. In this other slide, I'm showing you the pressure field distribution after the first fracturing stage and when you perform refracturing. So definitely a really nice tool to observe these cases and allows you to optimize hydraulic fracture processes. So as a summary, ZFRAC-RE simulation capabilities efficiently manage high-resolution models. We observe high-quality models, making it adept at handling definitely intricate details driven by observations. So here, the idea is to include those in the name of, for example, rock discontinuities, and see how they actually influence for growth and production. But not only those discontinuities, but also the key physics like stress shadowing effects, in many other phenomena that happens. So these effects encompass various aspects including how they actually influence growth, interactions with discrete fracture networks, and the most important part, the representation in reservoir simulation using EDFM. So here the computational efficiency of ZFRAC-RE is definitely boosted thanks to EDFM. That's all from my side. Thank you very much for your time. And if you have any questions, I will be happy to answer them.
Thank you so much, Joseph.
Thank you. If we don't have any other question, we can go to Chushi. He will show us more applications and a closer feel of ZFRAC-RE.
Okay, perfect.
Okay. Right. Thank you, Joseph, for the introduction, and thank you very much, SPE TAMU, for inviting us for giving a talk about ZFRAC-RE and the AI features that we have. So let me share my screen here. Everyone see my screen?
Yes, we can.
Okay, so my name is Chuxi Liu, and today I will talk about ZFRAC-Ai, EDFM-AI workflow, and their application for efficient and automatic fracture geometry calibration. So this is the overview of today's presentation. I will briefly discuss the general workflow of the ZFRAC-Ai, how we couple artificial intelligence algorithm with the ZFRAC fracturing simulation, and showcase some of its application in the field. And also, I will introduce the EDFM-AI workflow. Based on the ZFRAC-AI workflow, we can obtain the wetted fracture geometry, which may not contribute all to the production. So we use EDFM-AI workflow to calibrate propped or effective fracture geometry, and also some of the field applications. I also want to discuss some aspects regarding the GPU-based reservoir simulation to speed up the whole calibration process and help us better understand the unconventional reservoirs. So let's first talk about the ZFRAC-AI workflow and some applications. So this is a general sketch of the ZFRAC-AI workflow. So we use the artificial intelligence for automatic calibration of fracturing simulation. And throughout many years of the development for this workflow, we have tested a lot of AI features. And finally, we use the optimal AI model, which is called XGBoost, for this entire workflow. And the ZFRAC-AI workflow really enables possibility to calibrate fracture geometry, the wetted fracture geometry, with some of the monitor data. For example, if we have field measurement of microseismic data, this MSE, or if we have any advanced data such as fiber optics measurements, or even production log, we can try to honor those field monitor data and use them for ZFRAC-AI calibration. So this is the workflow for the ZFRAC-AI. So first thing, for this workflow, we need some of the basic input information. For example, we need either the geology model that contains geomechanics property, like Young's modulus, Poisson's ratio, and stress information. Or if you don't have the access to like a 3D geo model, we also can support well logs format to input this type of information. And also, if you have like a generated natural fracture model, the discrete fracture network, you can also put that into our a workflow, and we have software interface over this as well. But if you don't have this model, we can skip that. We don't need to consider natural fractures. And then we also need some required information, such as perforation report of your completion job. Also, like the pumping schedule, the injection rate, the pumping pressure or sand concentration. We need these for enabling completion simulation. And then based on that, we go to the next step, which is we generated a lot of cases with ZFRAC initially, and we run this initial iteration process. And we observe if the simulation result covers the actual history data of the pumping pressure. For example, we need to calibrate pumping pressure here. And then we employ the AI, the optimization algorithm to learn from the input uncertainty and also predict the simulation outputs. So the uncertainty that we mainly consider here for ZFRAC-AI is the sum of the friction parameters that's associated with calibrating the pumping pressure. Also, we need to consider the effective number of perforation holes, because due to erosion effect during the completion, maybe not all of the holes are effective. And then we also need to calibrate the hole diameter, the shot hole diameter, to also account for the erosion effect. So we use AI algorithm to learn from the ZFRAC simulation, and this process is iterative. So each iteration, we filter out optimal samples to run for next iteration, so that AI algorithm can learn progressively from more added simulation from the ZFRAC. And then finally, for the ZFRAC-AI output, we can obtain and also quantify the wetted fracture geometry. We can visualize them in the software interface in 3D. We can also see what is the distribution for a cluster level half length and also the height value. And also we can see, of course, the calibrated pumping measure match from the workflow. So let me also introduce some of the applications that we have for ZFRAC-AI. So this first one is a deep shale gas reservoir with a complex DFN system. So here I have a short animation to show that ZFRAC is very capable to model the activation of natural fractures, which a lot of other simulator fails to do. So we also employed the ZFRAC-AI for this reservoir, and we successfully quantified what is the stimulated rock volume represented by the wetted fracture geometry, and we can quantify for these multiple wells, like 4 wells in this pad, we can quantify multiple wells, fracture half length, fracture height distribution. And also we have applied this workflow for another tight oil reservoir. And for this reservoir, different than the shale gas reservoir, this one doesn't have pronounced DFN found underground. And we didn't include the effect of natural fracture inside this model. And again, this is another well pad model, which is multi-well with 3 wells. So we also applied the ZFRAC-AI quantification for SRV geometry. And also we calibrated the pumping pressure, and we can see the variation of fracture, average fracture half length and fracture height across the different wells. And for ZFRAC-AI, we can also consider like some of the monitor data for us to better calibrate the fracture geometry. So for this one, we have another application of the coupling with the microseismic events data and use these data to better constrain the fracture geometry with ZFRAC-AI. So we, for this well, we actually inputted the microseismic data, and we used ZFRAC-AI to match the aerial spatial extent of the microseismic events. And based on these monitor data, we can better quantify the fracture half length, the fracture height distribution across the whole well. Okay, so that's a brief introduction about the ZFRAC-AI workflow. So we can actually take the geometry that we calibrate from the ZFRAC-AI workflow and continue to seamlessly to input into the EDFM-AI workflow for production history matching to see how much of the effective geometry is contributing to the production. So this is the overview of the EDFM-AI workflow. So it's the basic logic behind this workflow with also ZFRAC-AI workflow is very similar. We also use the AI model, which is the XGBoost algorithm, to automatically calibrate the reservoir simulation using actual production history. And this is really the foundation for any type of like model predictions or even design optimization we can do for based on the results that we get from the EDFM-AI. We need a calibrated model to actually do this type of prediction and optimization. So this is very useful. And besides that, EDFM-AI not only gives you a single realization of history matching results, it actually gives you multiple, like tens of history matching model that has low error, and also that's representative. So it's like more probabilistic approach than the fundamental like deterministic approach for conventional history matching methods. And we can achieve really good efficiency regarding the EDFM-AI workflow because we couple that with GPU-based reservoir simulation. I will talk about that a little bit later. So again, for this workflow, we have very similar plot with the ZFRAC-AI. And we can see here for the EDFM-AI inputs, it's a little bit different than the ZFRAC-AI. Here we need actually the fracture geometry. For example, we can take it from the ZFRAC-AI calibration results, directly put into this input. Or if you have any other like fracturing simulation results, we can also support that thanks to the powerful feature of EDFM. And we can consider any type of complex fracture geometry. And besides the fracture geometry input, we also need to consider the reservoir-related properties like the petrophysical properties, like the matrix porosity, matrix water saturation, stuff like that. And of course, the basis of our calibration is the history production data that we need to input here. And then we go to the next step, which is very similar with ZFRAC-AI. We also do here we pre-process the fracture geometry using EDFM. And then we couple with the reservoir GPU-based reservoir simulator to run multiple simulation runs in the initial iteration. And then we use the AI to learn the reservoirs model for this workflow. So the uncertainty parameter or the input that the AI learns will be a little bit different as well. Here we need to consider what is the effective fracture half length and what's the effective height. This might be like smaller than the wetted fracture geometry. And I will also show you how we get this effective geometry. And also some other uncertainties associated with fracture conductivity, fracture water saturation, so stuff like this. And again, we use these to couple with each other to do iterative workflow, so that the accuracy of the simulation and AI progressively improves. And for the output for EDFM-AI, we can visualize what is the actual drainage volume that's caused by the propped fractures. And of course, we can have the calibration results for the history match. And also, we can provide what is the probabilistic distribution for the effective fracture geometry for the half length and height. And actually, this technology, the EDFM-AI workflow, is actually highlighted by a 2021 Journal of Petroleum Technology. So just to showcase the entire workflow here. And regarding the effective fracture geometry, how do we consider that based on the ZFRAC-AI results or other fracturing simulation results? So here we actually need to consider a fracture geometry cutoff. So we use this module to generate the effective hydraulic fracture geometries. So here you can see, based on the first step here, we obtain the, for example, ZFRAC-AI geometry, and then we consider this cutoff like a ratio of the entire fracture, for example, entire fracture height. We base on the ratio, we remove certain part of the fracture height here, like the gray area, and we can play with this the height ratio so that we can generate different realization of the effective fracture height. So this is how we model the effective geometry. And currently, we're also trying to work on a new feature to perform the effective geometry cutoff, is to use a concept called the conductivity threshold. So we can assign a different conductivity threshold value. So below that conductivity, we remove the fracture section for those small conductivity part. So using a different conductivity threshold, we can also preserve the complex fracture geometry with different threshold values. So let me present one of the field case study that we use for multi-well with EDFM-AI. So this one, we have 4 wells inside this model. And for this reservoir, the subsurface really complex. It has a lot of natural fractures, smaller scale and bigger scales. We have even faults in this model. So we actually have a very strong feature to honor for example, the seismic interpretation from these natural fracture systems, like the seismic attributes here. And we have developed a feature that we can draw the fractures based on this image. So based on this module, we can generate a realistic DFM model using the original seismic interpretation. And also here we run 4 wells ZFRAC-AI. So for the 4 wells, we have around 20 stages for each well. And the ZFRAC simulation is really efficient. It's like 10 seconds to model each completion stage. And for the entire well, it only takes about around 3 minutes to finish for one realization. And this one, we of course considered the activation of 3D natural fractures that we imported from the drawing we had. And for the AI calibration, we calibrated all 4 wells pumping pressure. And we actually run only about 30 ZFRAC cases per completion stage. So in total, it spends around 2 to 3 hours to finish the calibration for 4 wells wetted fracture geometry, and we can see the calibration results here. And based on the ZFRAC-AI calibration, we directly seamlessly imported to the EDFM-AI workflow. And first, we established a base case reservoir model, and we use a GPU-based simulation. And this is a GPU that we employed. And it's like only 2 minutes runtime for around 0.4 million grid cells. And based on the CPU, the conventional way, the CPU reservoir simulator, this might be maybe 50 times more, like even 1 hour to finish this, or even more times, depending on your computer. So the workflow is really efficient with GPU-based simulation. And of course, for the EDFM-AI, we matched the history production, and we actually ran about 500 cases, and it took only about like 6 hours, less than half a day, to calibrate 4 wells actual history production. And out of this 500 simulations, we can obtain about 42 history matching solutions. So what you see here is actually 42 model simulation results put together. And you can see all of them are pretty representative of the actual history trend. And of course, we can calibrate the effective fracture half length and also the height. We can quantify that. We can also give you a probabilistic histogram of the half length and also the height distribution. So based on the most representative one, which is the P50 value around this distribution, we can give you also the most representative, the geometry. And for this case, we can see the fracture half length is around 30 to 60 meter here, and height is around 4 to 8 meters. And based on those 42 simulation of the history matching model, we can also do the EOR forecast to predict what is the 20-year cumulative gas production. And for this case here, we can see for all the 4 wells, we can predict pretty much all the EOR for these 4 wells. And also, we can see the pressure distribution, the dynamic pressure distribution. We can separately visualize them only in the fracture, and in the matrix, we can separate them. And we can obviously visualize the drainage volume after the 20 years forecast. Okay, so I want to introduce the GPU-based reservoir simulation to greatly speed up our calibration process. So first, before I go into details, I want to briefly talk about the basics of the GPU computing. So traditionally, for the reservoir simulation that we use CPU computing, and this is not like very ideal for large model, like million level grid cell model or big size of data set. And but for the GPU, it's actually the future of computing, and we have already seen wide applications across different industry. The reason behind this is that for CPU, for each computer, the number of computing cores is actually limited. Like the most common laptops, they only have 4 cores or at most 12 cores. But however, if we compare that to GPU, we can see actually GPU actually holds thousands of computing cores. And previously, GPUs only designed for graphics handling, like your video games. It's only designed for that. But the founder of NVIDIA here, which is a prominent GPU company that is very popular now, the founder of the NVIDIA, the Jensen Huang, actually is very smart. He said, like, maybe we can try to also use the GPU for maybe scientific computation, something like that. And now it's like very popular for GPU computing because the computing power based on this comparison is very prominent. And so for GPU's reservoir simulation, the performance of this is actually grows directly with the bandwidth. What is the bandwidth? So this one, the full name is actually called memory bandwidth. So this measures how fast the data can transfer. So as you can see here, we can observe a very linear trend between the memory bandwidth here, as you go from left to right, and also the normalized speed. And actually, this is actually the bottleneck of the reservoir simulation is actually how fast you can transfer data. Like, for example, your milling level grid cells. And also another aspect for regarding this is that the peak memory bandwidth of GPU actually grows exponentially. So in this plot on the left, we can see for the past like 15 years, the CPU memory bandwidth is actually kind of stagnant. It's like a kind of linear semi-exponential growth. But for GPU, if you look at the green curve, it's actually quite faster growth rate compared to CPU. It's like true exponential growth rate. So this means that GPU computing will be big in the future because as we go along into the future, this speed will also skyrocket. Okay. And another thing about the capability of the GPU-based reservoir simulation versus the traditional CPU-based is that it has a really outstanding bandwidth. So for this test, we have 4 A100 GPU, which is really, really fast. We can couple these 4 like multi-GPU together to run reservoir simulation. And based on this, we can see that the memory bandwidth is 8 TB per second, which means you can transfer 8 TB of data per second, which is really, really fast. And in order to achieve the same memory bandwidth, we need to employ around 1,280 cores. So as you can see, this is difference is very, very huge. So next, I want to present our EDFM coupling with GPU reservoir simulations, some tests we did regarding the efficiency and also the accuracy benchmark. So this first test we did is actually a shale gas reservoir. We can see we have the realistic geomodel. We have complex natural fractures. We also have like hydraulic fractures for this horizontal well. This is the detail of the model. I won't go into all of these. But I want to show the results here we have. So we can see for the simulation results on bottom-hole pressure, different flow rates, and different cumulatives, it's all matching very well with the other simulator, the CPU-based simulation. And we can see here for the time spent between the CPU-based simulation and the GPU-based, we can get a speed up of 40 times. So the CPU-based is like 30 minutes, and for the GPU-based is like less than a minute, only around 40 seconds. And this one is another one we had the test for the speed and accuracy. And this one is a carbonate reservoir with water intrusion effect. And we also compare with the different simulator and we get identical results. And here we can see the speed up for this case is also very huge. Like for the CPU base, it takes around 8 hours to finish, but our simulation is only around 15 minutes. And this is another shale gas application. It's a 6-well pad, and we also compare the efficiency regarding this case. And this one has a really long history, like 8 years of production data, and it only takes about 8 minutes to finish the whole model. While for CPU case, it's like 2 hours. And also for the GPU-based reservoir simulation, we can couple different GPU, like multiple GPU, to form a parallel GPU run. So we also tested a huge model. It's like 250 square kilometer model. And for this model, we have around 60 million grid blocks, so a lot. And we have about 100 horizontal wells. And for this case, if we employ the 4 GPU parallel, we can finish only in 2.5 hours, which is really, really fast. And for the traditional CPU-based simulation, I also tested this, but of course, it didn't finish in time. But my estimate based on the simulation that I did is around at least 2 weeks to finish this entire model. So you can see a drastic increase from CPU to GPU. So that's all I want to say regarding my talk. And to wrap up the talk, and for EDFM-AI and ZFRAC-AI, we can perform a more probabilistic calibration to capture the uncertainty, the intrinsic uncertainty with fracture geometry, and we can rely less on a deterministic single model for this calibration. And ZFRAC-AI and EDFM-AI can really help engineers better evaluate, understand fracture geometries, their completion effectiveness, and this is a foundation for any future model prediction or even design optimization work. And for the efficiency, we can see clearly that when coupled with EDFM-AI GPU, most of the scenarios we can finish within 1 day. But previously, we also coupled this with CPU, the conventional reservoir simulation, and this process is time-consuming. It's like multiple day projects. And for the accuracy, for EDFM-AI GPU and compare with EDFM-AI CPU, it's like similar or sometimes even higher accuracy, because given in the same amount of time frame, GPU can run much more case and can calibrate the uncertainties much better than the CPU-based workflow. Okay, so thank you all very much for listening to my talk. And if you have any questions, we can discuss now. Thank you.
Great, thank you so much. Yeah, actually, we got some questions in the chat box, and I can maybe start with them. So the first question, it might be also like from the previous presentation as well. So the first question is, how many information have you guys applied for the ZFRAC-AI workflow?
This one. So we have applied this to some of the shale gas reservoirs in Asia, in China, and we have also have I think mainly in applications in Asia, the ZFRAC-AI application here. Maybe Dr. Wei, if you have anything to add, we can add here.
The first ZFRAC-AI and EDFM-AI, we work with like several US company. We did some projects for the Permian Basin. We have like a Wolfcamp A, Wolfcamp B somewhere to calibrate fracture to understand effective height and half length to optimize well spacing. So we have a very good data set for Permian Basin. And secondly, like Eagle Ford Basin, because the Eagle Ford, we work with the company to do gas EUR. So they must understand the well interference, because when you perform natural gas pumping half and half, you cannot pumping like a single well. You must consider multiple well and the interference, and maybe you pumping one well and you need to shut in the neighbor well. So that's help a lot for gas EUR in Eagle Ford. And of course, when I'm a PhD several years ago, we used this one for Marcellus Shale, for shale gas reservoir. And recently we try to move on to the Bakken reservoir. I think yesterday, Dr. Liu, we discussed with another oil operator for the Middle Bakken, try to test this. And recently I also contacted some other operator. They want to try, because based on the GPU and the AI, we can save a lot of time. Simulation, some people said maybe no simulation is correct, but we still make sure some simulation is useful, because I know one expert, like his name is Box, he said all models are wrong, but we need to make sure some models are useful. So I think if the model efficiency cannot be improved like today, the efficiency, the speed, I think it's difficult to use for the real application. I talked to some manager from the oil company. If you hire one master or PhD to work on simulation, you spend several months to calibrate the model. Maybe that's too late. So we really need timely to make sure model quick calibrate. You give me the data, we can match the monitor data maybe 1 week. So that will be very cool. Will be very useful. Of course, we have a lot of other Middle East and shale gas reservoir, and also Asian, something like shale gas reservoir, because shale, because the U.S. lead this area is a revolutionary development for unconventional. So many countries and they learn from U.S. development. For that reason, we have some market in other countries.
Okay, perfect. Thank you. We have another question, which is, how long did it take for automatic calibration in an average? This is for the ZFRAC-AI.
Yeah, so most of the scenarios that we have for one well, it's like just several hours, like 2 to 3 hours. So ZFRAC is really efficient fracturing simulator, and one completion stage is can run below 1 minute, like seconds level. So if we run ZFRAC-AI, even though we run multiple cases, like tens of cases, still it will take around like several minutes to finish one stage. And for one well, that would be around like 1 hour to 2 hour level in general. Yeah.
Okay, perfect. Right. Next question. Have you guys used fiber measurement for calibration in any of the formations in the US? If so, can you share the formation name and some findings that were surprising for you?
Maybe I can help answer the question. So that's I really found now we try to do one project to considering fiber monitor, but before that, not many operators they have fiber monitor data. But recently we have a very good opportunity to work with the company to do that. So I think maybe next time if we finish that, we can maybe have another presentation for it. But today we don't have real data to show this here.
Okay, perfect. About EDFM-AI, do we need to generate training data by changing uncertain parameters and build proxy model for history matching? So someone is curious about how the uncertain parameters are calibrated during history matching process in details.
Yeah, so first we need to understand what uncertainties parameters we need to consider, right? So of course we need to consider what is the effective geometry. So what fracturing simulator, the ZFRAC, tell you it's like a wetted fracture geometry. And but of course, maybe not all of that geometry is actually contributing to production, because during the production, the fracture closes because of the pressure change, and some part of the fracture, they have maybe very low propant concentration, and those parts, the fracture will be closed. So how we can understand better the effective geometry, the effective fracture half length and height, of course we need to consider this as uncertainty. This is like the dominant factor in unconventional reservoirs. So we need to consider that. And for the AI, we just learn from the basic idea behind AI is that we learn from the reservoir input, like this uncertainty. Based on sampling and the value, we learn from the input, and we predict the output for the reservoir simulation. And iteratively, we progress, we learn from the AI, we do more simulation, and this is the general workflow behind the EDFM. Maybe Dr. Wei, if you have anything to add.
I think for uncertainty, you can share your screen, show the Permian Basin. So that including all the uncertainty, including, that's good. From matrix, hydraulic fracture, and relative permeability, because the unconventional oil is difficult to measure relative perm in the lab at some natural fracture. So that's the key summary here.
Perfect. That's great. All right. Next question. What's the advantage of this algorithm compared to traditional history matching algorithms such as genetic algorithm or ensemble-based algorithm?
Maybe I first answer, maybe Liu, you can help comments. So the key advantage of this workflow, because automatic history match is not quite new, it's many years. For conventional reservoir, we can tune a lot of uncertainty. But for unconventional reservoir, maybe Liu, you can stop that slide. The Permian slide, the last slide. You will see that the key difference between this workflow and other commercial workflow is hydraulic fracture. So for hydraulic fracture, like Liu mentioned many times about the cutoff. So if you, because we have EDFM, most other workflow, they don't have EDFM. They maybe couple unstructured grid. So if you want to change effective fracture geometry, you want to trade off the height or half length is quite challenging, especially you honor the fracture geometry from a hydraulic fracture model. So it's very difficult. So that's the key advantage of our algorithm. We have EDFM, we have a cutoff. We can easily to change the fracture size. That's the key advantage. Otherwise, if you don't have this algorithm, it's difficult to tune this hydraulic fracture geometry, because for unconventional, the key dominant parameter is the hydraulic fracture size and conductivity. So that's the key advantage. The other is similar, like matrix and relative perm. All other workflow, I think they can honor this.
Okay, perfect. Thank you. And the last question that I have here in the chat. So you compared speed with a complex CPU and complex GPU model, but do you have any comparison of accuracy between complex GPU model versus a simplified CPU model?
Yeah, in these slides, I have shown the comparison between the results, the simulation results between CPU and GPU. So we did a lot of benchmarking for the simulation results, test the accuracy. And you can see here for different parameters, actually it's identical match between these two types of simulator. And also for this case, we can see the identical matches.
Okay, perfect. All right. Do we have any other question from the audience? Okay, we have another one here. It was mentioned that the model generates a probabilistic estimates Is there a point in the simulation where one can input the input distributions?
Yeah, so so for EDFM-AI here, so for the initial iteration that we do, we assume a uniform distribution. So the priority distribution is actually uniform distribution, and that is assumed by default. And however, if you are but most of the cases actually like uniform, when we assume the uniform distribution here for the initial iteration, it can handle the posterior pretty well. But however, we also have the flexibility to play with that, but we didn't add that feature here yet. So for now, we just assume the uniform priority distribution for EDFM-AI. Yeah.
Maybe I can give some comments. So this question I got when I talk about EDFM-AI, because we use MCMC Monte Carlo method to do sampling. So MCMC advantage is that if you don't need to tell the initial distribution, you can assume any distribution like uniform is okay, but no matter which distribution you input, after MCMC sampling, finally they will converge the real distribution. So that's the advantage of the probabilistic method of MCMC sampling.
Thank you. All right. I think with this, we come to an end for the session today. Thank you for all of our guest speakers today, and thank you for Dr. Miao for his effort and help in organizing this event. On behalf of TAMU-SPE, we really appreciate all the time and effort, and we encourage all of the students to maybe contact us so that we can provide some emails for the students who want to maybe request any license for their research related to the software. And I'm glad that you guys accepted to provide the license for our students. So again, thank you so much for everyone who attended, and thank you, Semtech, for all the great session and the support to our chapter.
Thank you, Kasem.
Thank you.
Thank you.
Thank you, everyone.